what would I say? What's my domain for this function? X such that, where are we? Yeah. Okay, so if you wrote it as an inequality notation, you'd go between -3 and 6, but you don't. It's kind of hard to see because of the line on it. Remember that that open circle means I don't include it. If we wrote it in interval notation, we would say I'm going to go from -3, and all the values from -3 to 6 would be where this graph would be squished onto the x-axis. And if you use the horizontal lines, again, these are just kind of visual help tools. If I use the horizontal lines to talk about values of y that define my graph, now I'm in between these values of y, the highest point on the graph, the lowest point on the graph. And then that would be used to write our range values. So thinking about what I've got there, again, I've got an open circle. So y such that, what would this one be? What are my range values? Less than 4, greater than or equal to -5. Yeah, there you go. So again, as an interval, we can be bigger than or equal to -5, so that's included. But we got to go to 4 and not include it because, again, that's an open circle. So there we go. Tool. Yeah.
So the line and like like how the line is sitting on the line. Like the red line is sitting on the black line, but it's not touching the graph, so that always is.
Are you talking about this line right here?
Yeah.
How it's not touching what?
How it's not
the dot?
Okay. It's touching the line.
Yeah.
Always included.
What is what always included? The -5?
Yeah.
Yes, because that's actually a physical part of the graph. If I had a point of discontinuity or a hole in my graph, I'd have an open circle right there. And that would be the only time when I would include it. Okay.
Do you have to write the x such that, or can you just write the credit?
Yeah, this is more of a formal way. So if you just want to write domain and then from -3 to 6, is that what you're asking me? That's okay. All right, how about that next one? What are we going to do over there? What would you write as domains for that graph? Again, you use the vertical arrow, vertical lines. Think about where does it start, where does it stop? Starting right there. But I've got an arrowhead now, so I really don't have any other place to put this second vertical line. So what must that mean? Domain. Yeah, so this is like, it looks like a radical function there. So again, I have an open circle on -4, and then the graph just keeps going to the right. So I don't include anything to the left of -4. But I can say from -4 to infinity. That would be that domain. Think about the range. There again, I'm limited there. That's the lowest point of my graph, and everything above it. So what's that one going to be? -2 and infinity, yeah. It just keeps going. So that defines all of the values of my graph. Again, think about it being squished. X-axis squished on the y-axis. So just a visual tool. I don't know if that's good for you guys or not, but just a way of thinking about the domains and ranges. And again, it's easier when you see the graph. When you don't see the graph, it's not as simple to find the domain and range. All right, that last one. Alex, what do you think? What's the domain on that? B. All reals. Yeah, because it keeps going, right? Domain, x equal all reals on this. Range. Who's got it? I think you have a range for that one.
Y is greater than or equal to 1.
All right. Y is greater than or equal to 1. Again, if I'm going to use interval notation, 1 to infinity. All right, so that's kind of where we're headed today in terms of the domain and the range part of this. So looking at these graphs then, why don't we quickly come up with this. Okay, so we've got all reals for both of these. That's a cubic function that's been moved over to the right. All right, now this next one shows what we're going to be talking about here a little bit. It shows a point or value, a range of what we call discontinuity. The graph is broken. This is a piecewise function. All right, who's got the domain for me here? Miss Bobby.
X is greater than or equal to x degree. Sorry.
Bingo. Greater than or equal to 3.
And then infinity, so it's a bracket.
Okay, so we've got a bracket on 3 going to infinity, so it's going to look like that on that side.
And
Parenthesis it.
then parentheses infinity.
Okay, we're going to go to, oops, not that. Negative infinity to, where are we headed? Where are we stopping?
Negative.
-3. All right, now there's one other thing I need to do with this. What do I need to stick in between them? A union symbol. That would define all my values of x. All right, new person, range. Let's go, Mr. Hulsus. How about it? What's the range of this thing? Think about squishing that graph on the y-axis. What's going to work? Not like infinity, that works, yeah. Positive infinity works. What about going the other way? Yeah, it is. So how do we say that? Usually, we could say it as a negative infinity to a positive infinity, but we say it a certain way. All reals. Yeah. So you take this open point and set it on the y-axis, but you have this closed point that comes over and overlaps it. That means y equals 0 is okay. And then everything else is okay too. It's just taking this first graph right here and just pulling it apart horizontally. That's all we've done. All right, new person, domain on that third one. Do I have to kick somebody? You're not going to volunteer, really? Thank you, Mary Francis.
Oh no.
Oh, okay, squish. Do you like the squish idea? It doesn't make any sense to you? Okay. Do you see that there is definitely, in the x direction, a beginning point to this graph? Okay, and where is that beginning point?
-1.
Good. And so if it's a beginning at 3, -1, and it's going to the left, what does that tell me my domain has? Because here's what I'm doing. I'm taking all the points on this graph and I'm drawing them down or up to the x-axis. So what's going to work for this thing? To what? Well, I don't need to do the -1 because that's a y value. I'm just talking about the x values. So I'm going to go from negative infinity to 3. Those are all the x values that we find. Yes, sir.
Why did it bracket the code the full dot?
Yes, it's a closed circle, so we include it. Yes. Okay. All right, what's range?
Y such that y is greater than -1.
So now the lowest point on the graph is -1, and then it's going to go everything above that the graph's y values, this is the smallest y value. So again, imagine all these points being drawn over to the y-axis, right? This thing would just keep going. As that arrow is getting bigger left and right, all of those points would define values of y. All right, this is what we looked at yesterday at the very end. And this is just a review for our parent functions, and I'll let you guys go back and peruse and check this out at your own leisure. But we had 6 parent functions here, 2 more that we don't represent, a log function and an exponential function. So you go check these out. We talked about the domain and ranges of all of it as well. So go peek at that. But now here's what gets hard, is when there's no graph to look at. And how do we take care of this no graphic thing? We looked at yesterday rules, 2 of them. When I have radicals and when I have quotients. I have to be careful of those with my domain. So let's try and do it without the graph. And then if we get stuck, we can throw the graph up there really quick and then see what our domain would be. So this first one, well here, I want you guys to try them first. Let's see if you guys, well no, then we'll do some, you guys can try another one on your own here in just a second. So does anyone remember our rule for the square roots? What did we say for square roots, domain-wise? Yes?
Has to be greater than or equal to 0.
Has to be greater than or equal to 0. Can't have a negative underneath there. So we go back to sign charts if we're thinking about greater thans or less thans. And that would mean that the radicand, the thing underneath the radical, we would set greater than or equal to 0. Now, since this one only has one value of x, it's not x squared or anything, I really don't need a sign chart. Because if I just solve this for x, move the 3 to the other side, there is my domain. Those are the only values of x that I can plug in here and then get a real number. 3 minus 3 is 0, 4 minus 3 is 1, 5 minus 3 is 2, and all of those I can take the square root of. If, however, there was a negative 2 or a 2 in there, negative 2 or 2 minus 3 would be negative 1, and I can't take the square root of a negative 1. So just by solving the inequality, I get the domain of a square root function. And again, this one has just a single value of x. So my domain would have to say from 3 to infinity. That would be the domain of this one. What does it look like? Well, it's a graph that starts at, no, not that. Don't want to move that. There we go. Let's move our little bubble over. Not this thing. There it is. There's your sideways part of a parabola. Look where it begins at 3, and then it just keeps going to the right. Switch it onto the x-axis. Everything is 3 on. I'm going to have a part of this graph. Okay, now the rules don't change. Second problem, I'm still under a radical. I do the same thing, but this one gives me 2 x's, so now I got to sign chart this one. Right? Sign chart this guy. Help me factor it. What am I going to do when I factor x squared? Because this has to be greater than or equal to 0. So what's it break down to? Good, plus 6 minus 1 has to be greater than or equal to 0. So now remember, when we sign charted this stuff, what did we do? We found the, what do they call it? Well, yeah, there's special things we call them. No, not vertex. Yes. Zeros. We found the zeros of this quadratic, and the zeros help me define my sign chart. So the zeros of this quadratic are negative 6 and 1. X plus 6 equals 0, x minus 1 equals 0. Negative 6 and 1. My sign chart, negative 6 and 1. And what am I looking for on my sign chart? Which sign? Still having a hard time with this idea? The whole idea of what sign to look for? How do I know? It's bigger than 0. Things bigger than 0 are positive. Things less than 0 are negative. So I'm looking for positives when I do my sign chart. All right, plug a negative 7 in. On the left, I get a negative 1. On the right, parentheses, I get a -8, and two negatives multiply together to produce a positive. I want that. Put a 0 in, I get a +6 and a -1, which makes a -1. Put a 2 in, I get a positive and a positive, which makes a positive. I want that. So what's my answer? What's my domain?
-6, 1.
Be careful. Be a little more specific for me. How am I going to write it? Because if I said -6, 1, I don't know what that means.
Domain.
Well, okay, that's true. We are going to have domain. So we're looking for domain.
X is.
Okay, look at the pluses. Where are the pluses?
On the outside.
Okay, so explain that. Describe what that means.
Would it be -infinity, -6?
Exactly. -infinity to -6. Close it on a -6 because I can be equal to 0 there. Union with
bracket 1.
1 to infinity. There you go. There's your domain for that guy. So what does this thing look like? This is not your typical radical function because I got a quadratic underneath it. So it looks like, oh boy, I knew that was going to happen. It looks like this. What? Yeah. It's half of the sideways hyperbole. Well, our conic section. So it looks like that. And look where it goes. It goes from -infinity to -6, and it stops, and there's nothing. And then it picks up again at 1 to infinity. And there's the domain of my graph. Go figure. Disconnect. Probably not going to do it. Too close. Man. What's going on? Okay, we did one of these yesterday. Describing the domain of this thing. It's also under a radical. So Braulio, how did I set it up? It's under a radical. Every time I set it up this way. Never a mystery. Perfect. It's greater than or equal to 0. It's got to be. So I have to say that x minus 3 and then x plus 6 must be greater than or equal to 0. All right, good deal. So what am I using with this? Inequalities. What do I use? What? Okay, I gotta find zeros and asymptotes. That's really not what I'm looking for. What am I gonna use? Inequalities. Sign chart. I gotta use a sign chart. I have to use a sign chart every single time I have an inequality. So, okay, now this one's a little more unique because in the first two there were no asymptotes to worry about. No denominators that had variables. This one has a denominator that has a variable in it. And so that's when we go back and we recall that up in the numerator I find zeros. And in the denominator we find vertical asymptotes. And I can't be vertical asymptotes, meaning I can't ever equal that value. Because if I did, I'd get undefined. So I'm not going to be, when I set up my sign chart, I will never ever be a bracket for a vertical asymptote. They are always parentheses. Okay, so Austin, you said zeros. So what are my zeros for this function? There's only one of them. There's only 3. There's only 3. And then I suggested, so you don't forget that you can't include it, put a circle around your asymptote. And now we just sign chart it, just like we did before. So put something in here. Tell me what I'm going to get on the left-hand side, please. Okay, good job. -7 would make a -10 over a -4, which is a positive value. Zeros would give me a negative, and then 4 would give me positive. So there I see my answers. What do you think, Sam? What's my answer for this one? parenthesis, negative infinity. To negative 6. Be careful. Oh, good job. Parenthesis, union symbol.
Bracket 3,
Oh, yes. Love it. There you go. There's your domain. If I took this graph, when I graphed it, and I switched all the parts on the x-axis, those are the only parts that would hang out on the axis. Here's what it looks like. Another weird one. Look at that. So we're not being able to see this, but remember how we said x can't equal negative 6? Look at this. Look what my graph does right near negative 6. There's negative 6, which is a vertical asymptote. My graph will go right next to it and hang out there the whole time, but it won't ever cross it. That's amazing. All right, so sometimes, again, if I have the ability to put a little t table together, pick plenty of x values to see what my graph looks like. You can sketch it and kind of see. But it's probably easiest just to remember our 2 rules. What are they for domain? What are the 2 rules? Okay, that's one rule. What's the other rule? No negative where? No, denominators can have negatives. You can't have negatives underneath the radical of an even radical. So your answers for domain of problems that have no radical, but just x is in the denominator, will always be x can't equal your values that are in the denominator. When you have a radical, your answer will always be a sign. Something greater than or equal to less than. Okay? What do you have? Questions? This is again the hardest part. The domain and the range is the hard part. All right, I think the rest of this, once we get through this in discontinuity, I'm going to kind of let you go because the rest is just for you. So this concept of a function and whether it is increasing or decreasing or staying constant has to do with the shape of it. And again, we talked about slopes when we were doing linear stuff. We said if I walk left to right across a graph and I'm going uphill, that's an increase function. And if I go downhill, it's a decrease function. And if I stay flat, we call that a zero slope, but that's the same thing as a constant in our function. And so you can see here that you got some functions that have a little bit of everything. Hello? So sometimes we get everything in the function, and these would be functions that are known as piecewise functions. So for example, this dude right here, that's a piecewise function. That was created from 3 different equations. 2 linear, well, they're all linear actually. 3 linear equations, where 2 of them have non-zero slopes, and 1 of them has a 0 slope. And that function there has everything. It has a part of the function that's decreasing. That's happening from here to here. That's a decrease. And then, from here to here, what's the function doing? It's constant. That's constant from there to there. And then, from here to, well, it just keeps on going. I am increasing. So when we think about increasing, decreasing, constant, you're only considering the x values. What are the x values that make that happen? So what would you say on this one? What's happening with that function? It's what? It's increasing. It's constantly, well, I shouldn't say that. It is getting bigger in the y direction as x gets big. I'm walking up the hill. That's an increasing function. Now I know you're thinking, you guys are freaked out because you're looking at that and you're saying, but wait, that arrow means it's getting smaller. Is that what really that means? No, think going left to right. Who cares if the arrow is pointing down? It just means that graph just keeps going in that direction. But as I go left to right on the graph, I'm moving up. I'm moving up the hill. So I'm having an increase. Okay. This one. Again, thinking about the x values that define where these things happen. What would we say? What am I doing with that function? I'm doing a little bit of both, aren't I? Doing both. I'm walking up the hill, checking out the view from on top of the mountain, then I'm walking back down. So if I'm walking up the hill, I'm increasing, and I'm walking down the hill, I'm decreasing. And again, we're going to express it as an interval. So if I'm going to say, where am I increasing? We would say, well, that's going to happen from negative infinity to 0. And where are you decreasing? Oh, that's going to happen from 0 to positive infinity. So we think about just the x values of this. Okay, what about that one? Oh, look at this one. What's going on here? What's that thing? Parabola. What do you say there, Jordan? What's the parabola doing? Any place where it's walking down the hill? Where? From where to where?
The left side down to the 7.
Good. From the left side of the parabola down to the vertex, I'm walking down the hill. And then from the vertex to the right side, I'm walking up the hill. So again, this one's like an absolute value. It's just not linear. You can have functions that aren't linear and still talk about where they're increasing and where they're decreasing. All right, let's pop the graph open, put a hole in it, and now talk about this thing called discontinuity. So we somehow break the graph up, and we get these gaps, and that's what we talked about as discontinuity. Now here's again, just like a discussion of increasing, decreasing, and constant, discontinuity is referring to the x values. So the x values that tell me where I have a gap, not y's. I care about y's, I just want to know where am I broken. Well, okay, and where am I broken on this first graph? Well, we've got two open circles. Where in the x value am I broken right there? What would you say? You're broken at x equal what? 0. You're broken at x equals 0. Right there, my graph takes this big jump. So at x equals 0, I have discontinuity. That's all. I don't care that it's a y value of, say, 1 or a y value of negative 1. That doesn't talk about discontinuity. We just want to know where am I broken. That's all. All right, am I broken on the second graph? Any place where I'm busted there? Nope, I'm not busted on the second graph at all. That's just a piecewise function, and everything connects with each other, so we're good. I got a little busted action going over there on the next one, though. So if I were to pick some values, what do you want to call that value right there? 1. All right, what are we going to call this value right here? 2. So where am I busted? How do we write this? Am I broken? You guys notice this is very much the same thing as domain. It's kind of the same discussion, except now we're looking for parts where the graph isn't existing. Domain, we look for parts where the graph is. 1 to 2. And how do I write it? Do I write it with brackets or parentheses? I use parentheses because they're open circles. So I'm broken between 1 and 2. Nothing's going to happen right there. Discontinuity. Questions? That's the new stuff. The rest of this is just... Yes, Sam? What's that? As long as it's... Is that what you've been thinking about this whole time, Sam? Really, Sam? That's very disturbing text. Just for that, Sam, you're not watching. Come Come on. I don't know if it's queued up. Let's see. Nope, it's still right there.
Try clicking play pause.
And I'm Alex Rocca. Welcome to your Friday, March 1st Bulletin Experience. Let's get started. GB
No,
Magazine
we're not
is...
starting, Alex. You just can't, Alex. We're not listening to you. All right, before we go and listen to Alex, because he's a little more exciting probably, I am not going to go over any of these other pieces because we have done this, and I don't want to beat a dead horse. So, well, maybe that's new, but I don't think so. So what I'm going to do is we're going to watch this bulletin because that's really what you came here for. That's what you live for. I live for the bulletins. And then if anyone has any questions on those, then we'll go. All right, Alex,
writing
take
a
it
story
away.
on the different cultural
Take it
foods
away.
that GBHS families make at home. If you would like to be mentioned in the magazine, email Mrs. Dixon at ldixon@rjuhsd.us. Are you missing something in your life? Look to the lost and found in student services for any material possessions you may have lost. Would you save a life if you had the opportunity? Sign up to donate blood with our nurse, Mrs. Warfield, in the health center. You must be 16 years or older to donate.
Hello, Granite Bay, Chase Down here. As you can see behind me, yes, there's a big gym, and that's where dodgeball will be held. Yes, Stephen Graber has a story. Oh, I got down to sit down with Stephen Graber.
Well, Chicks, on March 15, 2013, there's a dodgeball tournament happening. Uniforms are required. Both sexes are encouraged, male, female, of course. And the winning team is getting a cash prize for coming in first place. It's in the big gym. Bring your friends. Teams of 6. It's going to be a ball. 5 p.m.
So if you're thinking about getting any dodgeballs thrown at you, you can be there on March 15th in the big gym. Again, March 15th in the big gym. Any contact, call Stephen Graber. His number will be posted on Twitter. You can just get it at GBHS. Okay, this is Chase Stone. Have a good day, Granite Bay.
Congratulations to Speech and Debate on dominating the competition last week, and congratulations to the students who won a spot to compete at the state tournament in April. Get ready for Lip Sync on March 8th. Tickets will be sold next Wednesday through Friday and at the door. Tickets will be $8 for the first show and $10 for the second show. The superhero dance will be held on March 15th. Tickets will be sold March 13th through the 15th and will be $7 with activities and $9 without. Tickets will cost $10 for freshmen, sophomores, and juniors on Friday, and $5 each day for seniors as a reward for winning the superhero rally. Here's an ad with more information.
Who is your favorite superhero?
The Powderpuff Girls.
Why?
Because they're beautiful.
And who is your favorite?
Blossom.
Who is your favorite superhero?
The Incredible Hulk,
Why?
because he's really big and strong and green.
Who is your favorite superhero?
Captain Underpants.
Why?
Because that's the only book I can read.
Who is your favorite superhero?
Bernie Madoff.
Thomas, who is your favorite superhero?
My favorite superhero has got to be Deadpool.
And why?
He's really cool.
Hello, Granite Bay. I'm Jeff Howard. And did you know that the first ever superhero dance will occur at Granite Bay High School on Friday, March 15th? The freshmen will wear Captain America, sophomores Spider-Man, juniors Superman, and seniors Batman. So make sure to wear a costume and make it school appropriate.
Summer session credit recovery applications are now available. Students can see their counselor or the front desk to pick up a form. Due to the potential something